again, going back to this closed system, in a mineral crystal lattice, we want to understand this pi, and pi is the initial number of parents in that crystal structure. So so this is going to be at t equals 0, when there's 0 half-lives elapsed. When the system first closes, you're going to have some number of parent atoms. P is going to be our current number. So some time has elapsed, maybe 1, 2, 3, whatever number of half-lives have elapsed. Your initial parent is going to be something less. It's going to be the numbers you have currently, the current amount. And in the meantime, you're going to have grown some daughter products. So the current number of radiogenic daughter atoms. So with these, we can figure out ages of the system. So recall that at time 0, there are no radiogenic daughter, right? None of those. All daughter atoms originated from the decay of parent atoms, right? And so again, looking at our curve here, our goal is to figure out the fraction of the parent remaining, and then figuring out our number of half-lives elapsed, right? So we're going to use an example here that I've already worked out. Let's say in a crystal system, you measure atoms using the mass spectrometer, and you measured 88,214 parent atoms and 24,120 daughter atoms. So the first step, right, so I want you to pay attention because I have several problems that involve doing this, is to determine that fraction of parent remaining. And the way to get that, the fraction of parent remaining, is going to be taking your current number of parent atoms and dividing it by the initial number of parent. And so, but first of all, you got to figure out what this initial is. And the way to figure out initial, you just combine the parents and the daughters. Because remember, the daughters all originated from a parent atom, right? And so if I add those up, 8214, 24, 120, my pi is 32,334. So now I've got my initial. Now to figure out the fraction, right, I take the current number of parent atoms I have, p, and divide it by that pi, or the parent initial. And note that I get a fraction of 0.254. And here I'm using 4 significant figures because I have 4 here. I have a little more, but I'm using this lowest one. So now here is my fraction of parent remaining, right? So all I did is I divided that by that. Step 2, very important here, determine the t, the number of half-lives. And here I can use it with a graph, right? So here, 0.2540. So 0.2540. So if I go to my graph here, 4 would be a little bit above this. And so I'm going to have something right. So I'm going to have, if I bring this over to the graph, I'll see that I'm going to have a little bit less than 2. So probably maybe a 1.95. Again, it's a rough estimate, right? There's a better way of doing it. And the way I want you to do it is using this decay curve, right? It's more accurate. And the decay curve is the number of half-lives elapsed equals negative 1.443 times a natural log of the fraction parent remaining. So this is the natural log function. And so one key thing is your phones have, especially if you have an iPhone, you can remember to get the scientific calculator, you turn it sideways, and you want to be able to use this ln key right here, the ln key, right? And so let's figure this out. So I'll just do it here as we're looking at the problem. So remember, we had 0.2540, and then we want to take the natural log of it, natural log, and then I want to multiply that by 1.443, but it's negative, so see that plus minus, I hit that, so it makes it a negative, and then it's 1.97, a bunch of numbers. Remember, we only have 4 significant figures. 1.9, yeah, 4 significant figures is what I'm using there. Now, so these are the number of half-lives that have elapsed. So the next step is to determine the age of the sample. And so we need to know this T1 half. So we know T, remember T are the half-lives elapsed, but T1 half is the half-life of the isotopic system. So this is going to be something in years, right? This is going to be something in years, not in just number of half-lives, but in years. So you'll see that there are many isotopic systems, and each system has its own independent half-life, because remember, it's its own independent decay constant. Now, the important ones that we'll use are uranium-238 uranium-235 and potassium-40. Those are radioactive parents, and they're good for dating rocks. Carbon-14 is not really good for dating rocks because you need something that was once living, and besides, it has a very small or short half-life, so you really can't date anything older than about 50,000 years. So once you go, maybe 70,000, some people claim, but anything older than about 50,000 years, this system really doesn't work for because it has such a short half-life, 5,730 years. But for these other ones, you can see they're millions of years, right? So these are good for dating rocks of anywhere from a couple of million years old to billions of years old. Now, for uranium-238, it decays to the stable end-daughter product of lead-206. And one half-life takes 4.5 billion years, or 4,500 million years. That's one half-life. For uranium-235 to lead-207, it takes about 713 for this example here, million years. And for potassium-40 to argon-40, it takes 1,300 million years, or 1.3 billion years would be the half-life. So you can find this in your book. Table 10.1 has this. Now, if we go back to our example, let's say we're using the uranium-235 system, which decays to the daughter product of lead-207. And so that has a T1/2 of 713, right? So we determined our T, our number of half-lives elapsed. Remember, that's half-lives elapsed, T. So the age of the sample, so this is the final equation you'll need, the age dating equation, is going to be the half-life of that isotopic system times the half-lives elapsed. So we had 1.977 half-lives elapsed times 713. The age of the sample is 1410 million years.